Before proceeding further, let me introduce few things about this chapter. First of all, there was a scientist whose name was Dalton. He explained one atomic model. So that model was known as Dalton's atomic model. Okay. According to Dalton, atom was indestructible particle. Second, atom of given element are identical. And third, atom can combine to another atom to form new substance. What is the meaning of this? First, it is indestructible. Second, identical. Third, new substance. What is the meaning of indestructible? See, let us consider the example of chalk. That white chalk we used to write on the blackboard. Yes, if for the white chalk we take the last element that will act as atom. We can't further divide it. So according to Dalton, atom was non-destructive. Okay, then second, it will be identical. If I have a silver ring and someone else have a silver ring, if we examine the atom of this silver ring and that silver ring, the atoms will be identical. Okay, and two atom combine and form a new substance. Like if hydrogen combines with oxygen, we will get water. This is one substance, this is another substance, and if we combine we will get the new substance. Okay, then what happened? Then Thomson came and he gave his atomic model. Thomson's atomic model. Okay, Thomson's atomic model. According to Thomson, according to Thomson, atom is like a watermelon. Atomic model is like a watermelon. What is the meaning of that? Is according to Thomson, atomic model is like watermelon. In watermelon, what we have? We have a fruit part, and we have seed part, and we have a seed part. Okay, so according to atom, this fruit part are positive. This fruit part are positive charged, and this black part are, say, yes, negative charged. Okay, see, previously what according to according to Dalton, in atom we don't have anything, it's a non-destructive part. But Thomson came and he explained that nah, atom is not the last. In atom we have positive and negative charge. Okay, then total positive charge is greater than negative charge. Hence negative charge can not go out of the atomic model. This was the theory of atoms, Thomson atomic model. What advantages we have here? We have advantage that we came to know about the formation of ion, about the formation of ions. But what we don't know, what are the disadvantages? This advantage will be formation of ion. And what about the disadvantage? Disadvantages was distribution distribution of charge was improper. Okay, this first one was the Dalton's atomic model, second one was Thomson atomic model. Okay, then what happened? Then comes two students, Giger and Martin. This experiment will further known as Rutherford experiment. Okay, why it is like that? Let's see the concept one by one. Let's see the concept. What we have in Giger-Martin experiment. First we have a source of alpha particle. We have a source of alpha particle like this. Okay, from which alpha particles are emitting. Then from here alpha particles are emitting. Okay, yes. Okay, then what? Then we have a collimating lens. Okay, then we have a gold foil. Then gold foil are clamped between the two clampers. Okay, then behind this there was a screen, zinc sulfide screen. There was a zinc sulfide screen. and from two zinc sulfide screen there was a detector attached with galvanometer. This is electron detector. Okay, what is this? This is source of alpha particle. What is this? This is collimator. What is this? Gold foil. And what is this? Zinc screen. Zinc sulfide screen. Okay, then what? From source of alpha particle there was a beam of alpha particle emitted. To make sure that beam will move straight ahead, we will attach a collimator which will make sure that the alpha particle will be in straight line. Okay, then there will be a gold foil. How the gold foil will be? Gold foil will be very thin gold foil. Okay, why we can you how we can make the thin gold foil? We'll take a gold sheet and hammer it till we have a sheet of only single atom. There should not be a one more atom behind the screen, behind the gold foil. It will be clamped, and here we have a screen. Here we have a screen. Okay, now let's see the observation one by one. See what we will see here. We will see that most of the this zinc screen have the property that whenever the electron will going to strike on the zinc screen, we will see a scintillation, or the light will be there. Okay, we will see that maximum atom will cross here. Then maximum atom will pass like from maximum, like 80% will go from here. Okay, yes. Then this experiment was performing by Giger Marson. Actually, at that time, in 1911, World War II was going on. So they were actually designing the instrument to protect themselves from nuclear weapon, but they were experimenting something else, and they came to conclude. They came into the conclusion of this thing, which I am explaining you. Okay, what's the conclusion? We'll see. Then we saw that one alpha particle is passing around 90 degree. How much? Around 90 degree. Few were going straight line. Sorry, many were going in straight line. 10% was moving at 90 degree, around 90 degree. Okay, and one out of 8,000 was coming back for around 180 degree. See, going straight, it doesn't make any problem. Around 90 degree, Giger Martin thought that, yeah, we'll study on it. But this was very shocking to them. This 180 degree, return of 180 degree, that was a shocking part. So they thought about it, and they took this model and went to explain this same model to Rutherford. Okay, they went with this model to Rutherford, and they explained everything, that what were the conclusion. While Rutherford was performing experiment, he found this thing too strange. He was like, it one the coming back of alpha particle at 1 degree. It was so shocking to him. He gave the example, okay, it's like we are shooting to a mosquito, and that bullet is coming back. Why? Because see, it is not possible. Yeah, it is not possible. That see why? Because bullet is heavy, and mosquito is not that much heavy. So if that bullet will strike to mosquito, it can't come back. But here it is was happening, because see, even alpha particle is a heavy particle. Heavy particle doesn't mean that it will be of 1 kg, 2 kg, 5 kg, na. But in the atomic world, it's a heavy particle. So even he was shocked. Then what happened? He was studying and he came to conclusion about many things. He came to conclusion that, see, there is a nucleus. Around the nucleus, there will be an electron, and there will be many free space. See this one. There will be more free space. Okay, so the result of moving alpha particle in a straight line, it is because might be alpha particle will be entering here, 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 or here, like this something. Okay, yes. After that, one is moving around 90 degree. Why it is happening? So might be I'm making this with the red diagram, red marker. Might be because the new alpha particle would be coming here. Around 90 degree it will move. Okay, yes. Why? Because see, here we have a nucleus. It would try to come, alpha particle try to come here, but as alpha particle is positive and nucleus also is having positive charges, that's why it will repel and it will go like this. Then one out of 180 was coming back. Why it was happening? It was happening because that alpha particle would have attacked nucleus in the center, and that alpha particle would attack the nucleus in the center, and it was coming back. Okay, these three were the things. First one was maximum was moving in a straight line. Okay, one was moving around 90 degree. Why? It would have moved on a slightly lower distance. Then one at the center. Center means, yes, one at the center and coming back. Okay, yes. So that means according to Rutherford, nucleus is atom is not uniformly spread. There is a center part which is known as nucleus, in which entire positive charge would be there. Okay, then entire positive charge would be there. After that, what? Yes, we have electron which will be revolving around the nucleus. Okay, and in atom the majority of the weight is being concentrated in the center, and that center is known as what? That center is known as nucleus. Okay, yes. So let's see this thing in a theory part, one by one. Geiger-Marsan scattering experiment. In 1911, following the suggestion of Ernst Rutherford, Geiger and Marsan conducted experiment. They directed a beam of 5.5 megaelectron alpha particle emitted from radioactive source at a thin gold foil as shown with the figure which I shown. Okay, the setup involved collimating alpha particle through lead bricks, allowing them to fall on 2.1 into 10 raised to minus 7 meter thick gold foil. A rotatable detector with zinc sulfide screen and a microscope observe the scattered alpha particle producing light flashes or scintillation. Okay, a rotatable detector, that electron detector with zinc sulfide screen and a microscope was observed the scattered alpha particle producing light flashes or scintillation. Figure illustrated a graph of total number of scattered alpha particle at various angles. The theoretical prediction assuming a small, dense, positively charged nucleus aligned with experimental data. A significant portion of alpha particle passes through the foil without collision. Only about 0.14% of incident alpha particle scatter by more than 1 degree, and approximately 1 in 8,000 deflect more than 90 degree. Okay. Yes. Rutherford's explanation was, Rutherford argued that a large repulsive force must be present to deflect alpha particle backward. This force could be provided if the mass and positive charge of atom was concentrated at its center. The agreement with this hypothesis supported the discovery of nucleus and credited Rutherford for it. Yes, what according to Rutherford nuclear model? Rutherford model, this is important. Rutherford model persists that positive charge and most of the mass of atom reside in the nucleus. Electron orbit the nucleus at a distance similar to planet around sun. The experiment suggested a nucleus size of about 10 raised to 15 meter to 10 raised to minus 14 meter, significantly smaller than the known atomic size, 10 raised to minus 10, 10 raised to minus 10 meter. What about the empty space in atom? Considering the atom as mostly empty space, electron would be at a distance from nucleus approximately 10,000 to 1 lakh times the size of the nucleus itself. This explains why most alpha particles pass through a thin metal foil. However, when an alpha particle approaches a nucleus, the intense electric field causes significant scattering. Figure can be analyzed using Rutherford nuclear model. The thin gold foil allow assuming not more than one scattering event for alpha particle. Newton's second law and Coulomb's law are used to compute the trajectory of a single alpha particle scattered by gold nucleus. Coulomb law equation describe the electrostatic force of repulsion between the alpha particle and positively charged nucleus. The force magnitude is given by where r is the distance between alpha particle and the nucleus. The force is directed along the line joining the alpha particle and the nucleus, changing in magnitude and direction as the alpha particle approaches the recedes from the nucleus. Alpha trajectory, alpha particle trajectory. The trajectory of alpha particle is determined by the impact parameter known as b during collision. How you will define impact parameter? The impact parameter is the perpendicular distance from center of nucleus to initial velocity vector of alpha particle. The distribution of impact particle within the given beam of alpha particle, there exists a distribution of impact parameter b. This distribution results in the scattering of alpha particle beam in various directions with different probabilities as depicted. Scattering behavior, an alpha particle is close proximity to nucleus experiences significant scattering. In a head-on collision with minimum impact parameter, the alpha particle rebounds backward, denoted as Q near P. Conversely, with large impact parameter, the alpha particle undergo minimum deviation leading to small deflection, denoted as Q near O. Energy consistency in beam. In a beam where all particle share in a beam where all particle share nearly the same kinetic energy, the impact parameter influences the scattering behavior. Limited head-on collision. The observation that only a small fraction of incident alpha particle rebound suggests a scarcity of head-on collision. This scarcity implies that the mass and positive charge of atom are concentrated in a small volume. Rutherford scattering provides a powerful method to establish an upper limit on the size of nucleus. The limited number of alpha particles undergoes head-on collision yields insight into the concentration of mass and positive charge within the atom. Yes. Next is electron orbit. The Rutherford nuclear model of atom, grounded in classical concept, envision the atom as an electrically neutral sphere. This model comprises a minute, massive, and positively charged nucleus positioned at the center, encircled by electrons moving in dynamically stable orbit. The electrostatic force of attraction between the revolving electron and the nucleus act as a centripetal force, maintaining their orbit. This force balance is crucial for the stability of electron in their orbit within a hydrogen atom. For a dynamically stable orbit in a hydrogen atom, the relation between the electrostatic force and centripetal force is expressed as a given by equation. The relationship between the orbit radius and electron velocity is established as kinetic potential energy of electron. The negative sign of the potential energy indicate that electrostatic force is directed oppositely to radial direction. The total energy of electron in a hydrogen atom is given by the negative total energy implies that the electron is bound to a nucleus within hydrogen atom. If the total energy were positive, the electron would not follow a closed orbit around the nucleus, signifying a lack of binding.